So indeed, my name is Damien. I work in the HPC center in the university, UC Louvain, something like 30 kilometers south from here. And from our HPC center, we have seen the big data world slowly coming at us from far away, but every year, steadier, closer and closer. We've heard about the convergence, we've read about the convergence. And as I myself have a background in what we call at the time data mining, I don't want to be caught by surprise when a convergence would hit us. So I looked into the thing, and in the next 20 minutes, I will share with you some insights about concrete steps that we can, do I need to speak louder? Okay. About concrete steps we can take in HPC centers to make the convergence something concrete in the context of scientific computing. Because, you know, the scientists, they are never happy. Some of them, they have beautiful equations, they have models, but what they want in the end is to have data. Others, well, they have data, they have lots of data, but what they want is to have beautiful equations or to have models. Maybe you're wondering what Shrek is doing in there, and maybe you've seen in the previous slide there was a dwarf from Snow White. Well, the reason is in the literature, authors have looked at the kinds of problems that consist in going from data to models or from models to data, and they gave the name HPC dwarfs for those which are compute intensive, and big data ogres for the kind of problems that are data intensive. And when those ogres or dwarfs become too large to fit on the laptop, typically, it's not always the case, but typically what happens is that the dwarfs are moved to HPC clusters and the ogres are moved to clouds. And what people love or like about clouds is the fact that it's instantly available. You just click somewhere, as long as you pay for it, you have access to some resources. Also, it can be either self-service, where you manage your virtual machines, you manage your virtual networks, or it can be software as a service, where you just use your browser to access some resource and click in here and there, and you have your computations going, for instance. And I think about the cloud also is the elasticity, the shrinkage or increase in resources as you want, and the fault tolerance. When some resource fails, it can be replaced with other resource instantly. So the cloud is very versatile in a way. By contrast, clusters, they are close to metal, and people like the fact that they offer high-end hardware, dedicated hardware such as GPU accelerators and so on, and that access to the resources is exclusive. When you are given a set of CPUs, only your job is able to use them. So they are much more designed for performance than for versatility. But more and more, people from both sides have been looking at what the other sides had to offer. Interests from both sides are converging, and we can see that very clearly from public cloud actors, for instance, which all of them now offer an HPC solution in the cloud. So the main question I have, and I want to address here, is as an academic HPC center, what should we do to manage this convergence interest? Well, most large HPC center in Europe have started looking at at clouds, and so we need also to have a look at what the cloud can offer. To do that, I first need to review a bit what the cloud offer and what the cluster offer to see how we can merge both. A cluster typically is built on high-end hardware, costly CPUs, a lot of memories, very fast networks, very fast disks. And on top of that, you have the operating system. Most of the time with our DMA, use a lot to bypass the operating system and make sure that performances go from applications to the hardware very smoothly. And then on top of it, you typically have an MPI platform and a prioritize system, everything managed by a resource manager or scheduler. And on top of that, you have the HPC ecosystem, the user ecosystem. The cloud is a bit more versatile. You also have a layer of hardware here, mostly designed for commodity hardware, so no high-end clusters, no high-end CPUs, but entry-level processors, maybe regular network, regular disks, and so on. And then on top of it, you have the operating system, and on top of the operating system, you have the hypervisor most of the time, which is the layer that offers the versatility at the expense of the performances. And then I'm sure you know that, but the clouds have 3 levels of services classically. Infrastructure as a service level, where you can manage virtual machines, virtual networks, and block storage. And then on top, you have on the very top, you have the software as a service, mostly accessed by web or apps, where you just abstract the application away and just use it as a service. And then in between, you have the platform as a service, which can be related to the HPC platform in the sense that you have some storage solution, typically a distributed file system such as AWFS, and you have MapReduce or Spark or whatever frameworks in which you can perform your computations. And then it's all managed by a resource manager, and you already see that we will want to merge both stacks. There will be some conflict in the resource management because both stacks have one, and then you have the big data ecosystem on top of that. Just to make the big data and HPC ecosystem a bit more concrete, this is the list of typical things that are offered by both stacks. So in terms of languages, we see most of the time C, C++, Fortran in HPC. We see Java, Python, R, Scala in big data. And what you see here, just a list, but actually the ecosystem in big data is a bit more diverse than the ecosystem in HPC. And so there are things from the big data side that could be very beneficial in the HPC world. So now I'm going to detail 5 ways that cloud or big data technologies can be embedded into clusters or HPC. The first one is virtualization. So we can, with virtualization, bring more control to the users in an HPC environment and also bring more isolation. There are mainly 3 ways that we can bring this virtualization onto the cluster. First one is just to install your regular cluster stack and then on top of it install a tool such as Peacock here that allows spinning out virtual machines inside and Slurm allocation, for instance. So it's a way to add the virtualization on top of the existing HPC stack. You can work the other way around. It's often called HPC on demand or HPC as a service. First deploy on your hardware a cloud stack, and then inside the virtual machines deploy the HPC stack. And one tool that you can use for that, which is open source as well, is TrinityX. That uses OpenStack behind the scene to create virtual clusters that you can deploy for your users. So those 2 options are with virtual machines. The third one is to use containers. We've seen a presentation about Singularity just before. It's not the other option, but it's a very popular one. So containers are, at this point in time, very popular in HPC to bring the virtualization for the user and allow the user to have, for instance, a stack which is only available on Ubuntu running on a cluster where the operating system is a Red Hat, for instance. Second way we can use a cloud in HPC is through what we call cloud bursting. The idea is that when you have a HPC cluster available on premises and the demand or the request for computational power goes too high with respect of what you can offer, there are ways to use virtual machines provisioned in the cloud to make your cluster bigger and actually to bring elasticity from the cloud to the cluster. Every scheduler had this option now in Slurm. It's called the elastic compute. Yeah, elastic compute. You just define a set of compute nodes which are cloud, of type cloud, and then when your user requests more power, you can activate them, provision the virtual machines, and then they are seen from the perspective of your scheduler as additional compute nodes available for the users. Besides virtualization and cloud bursting, a third way we can enrich clusters with cloud technologies is to have additional storage paradigms. Typically, on a cluster, what you have to store your data is file system, maybe 4 or 5 different file systems, one which is parallel, one which is NFS, another one which is for archive and so on. But the cloud has to offer much more different storage types, and especially one of the big problems clusters often face is what we call the ZOT files problem, zillions of tiny files. The clusters are designed mostly to cope with very large files and a small number of very large files. But what we see more and more is users come with millions or billions of very small files containing very little information, and at the end storing more metadata than they are storing data actually. And so we think that by replacing some of the file system with object storage, such as HDFS or Swift or Ceph, we can try to move those users towards those kind of storage which are much more suitable for that. Another thing we can use is to have Hadoop connectors on top of existing parallel file system. Actually, most parallel file systems now offer, besides their typical POSIX file interface, an Hadoop connector that allows using MapReduce or other Spark workflows directly on top of the parallel file system without the need to install the HDFS. And finally, a last kind of data storing solution that can be useful in a cluster environment is all the ecosystem going from the NoSQL world. So maybe besides the file system, we need some Elasticsearch, or we need some MongoDB or Cassandra or InfluxDB or Neo4j to be able to store data in a way which is consistent and suitable to the type of data. So for instance, if you have graphs, rather than storing CSV files with a matrix of adjacency, you store them in a Neo4j cluster. And then we can have additional paradigms to our clusters, because typically what the clusters offer is an MPI stack, which is a way to write parallel programs, which gives a lot of control to the user, but it's also non-trivial to write correct and performant MPI code. And at the other end of a spectrum, there are job arrays. Many clusters just allow you to run job arrays, which are dubbed as embarrassingly parallel computing, because you don't have communication at all. So it's very easy to implement, but it's not very efficient. It's not very expressive in terms of what you can do with job arrays. And so the tools that are offered by the big data ecosystem with the MapReduce paradigms come kind of in between those two extreme, MPI and job arrays. And so there are several ways you can use those tools in a cluster. First one is to use MapReduce or Spark, for instance, in a standalone mode. I will not discuss this here because then you lose the interest of having several compute nodes that work together. What you can do is use a tool such as MyHadoop to deploy actually a Hadoop framework inside a regular job allocation, be it from Slurm or PBS or so on. Just a set of scripts that you call from your submission script that will spin up a HDFS storage and offer the MapReduce or Spark API for your workflows. You can go a bit further and try to disguise the HPC scheduler behind the big data or Hadoop platform with tools such as Anything on Demand or HAM or MacPy, which are tools that offer the MapReduce paradigm. And behind the scenes, what they are doing is just using the resources and requesting the correct resources from the resource manager just to make sure that you can use your scheduler as a Hadoop solution. Another thing you can try to do is to take advantage of the fact that the Hadoop solution, the Hadoop ecosystem is very fault tolerant. And so people have looked at ways to run the Hadoop stack on top of either nodes in a cluster. So when you have your clusters, some nodes are allocated to jobs, some other nodes are just waiting for jobs to come or for other resources to get freed. And you can leverage those idle tools and actually inform the Hadoop scheduler or the Yarn or Mesos of the idle nodes that come when jobs finish or that disappear when jobs start. And it's just a matter of playing with the prologue and epilogue files in your cluster just to be able to have both stacks. It takes away a bit of efficiency in terms of scheduling and in terms of computing, but actually people have shown that it's totally doable. And then the Graal, the far objective is to have a unified stack, big data and HPC, and maybe someday we'll have that. Some large actors are playing in the field and they are trying to develop something like that. I'm not sure it will come up as free software, but anyway, people are working on this. And then the final way is to enrich a cluster with web applications and allow the user, for instance, to submit jobs through a web interface rather than asking them to go through SSH. Sometimes for some people, using the command line is a bit of a hassle and they would prefer to be able to click here and there to submit their jobs, or to use tools such as RStudio or Jupyter to submit jobs interactively and notebooks and so on. And then also in the kind of software as a service thing of mindset, you can add some tools like Nextcloud to your cluster to allow your user to access the files which reside on the file systems from either their phone or from a web interface or with a desktop client, and make them able to share those files with people who do not have access to the clusters. So these are just 5 directions we can move to or we can progress to make the clusters look a bit more like something that is friendly to big data workflows and that leverage cloud technologies. And so if we were to design such a cluster now, what we would need is just to have nodes, compute nodes that have 3 distinct shapes, ones with very rapid SSDs and very fast local storage, ones with accelerators, either GPUs or anything else, some of them dedicated to GPU or to machine learning and deep learning, and to have some compute nodes with very high memory, and have the software stack on those compute nodes so that you can either run a regular job or something that is held in a virtual machine or in a container. And then besides your typical file system, you would have also nodes dedicated to databases, to NoSQL databases, which are the one depicted in green here. You would have the Hadoop connectors on top of your file system to make sure that the Hadoop workflows can work easily on the cluster. And then you would have 3 types basically of input nodes. The typical login node where user can use SSH to submit nodes and so on. But you would also have some web nodes that allow running RStudio or Jupyter to let the user use notebooks and those kind of interactive way of working with the clusters. And then some data transfer nodes that would have the same current tools such as GridFTP and so on, but also tools such as Nextcloud to ease the way for the user to share their files, and also the data transfer tools from the Hadoop stack. And so I hope that if we can one day do this, I just hope that we'll make scientists happy again. And I thank you for your attention.
Please stay seated for questions, otherwise it's going to be impossible for the noise. Please stay.
you.
Are you trying any of all things you showed? Are you experimenting with any of it?
The question is, are we actually doing what we say here? Yes and no. Yes, in the sense that every single piece has been tried somewhere at some place. No, in the sense that for now we are still not offering a single user interface for all these services. So we have Nextcloud somewhere, we have RCDO some other place, we have a typical cluster, we have my Hadoop, but we don't have a single cluster that offers all things at the same time. But it's what we tend to achieve, we try to achieve.